blocking my PowerPoint, right? The-
No, we can say it fine.
Okay, good.
Okay, so welcome everyone. Today's speaker is Dr. Jude Salinas, and he's currently an assistant research scientist at NASA Goddard Space Flight Center, and he works with NASA Goddard through the Goddard Earth Sciences Technology and Research Program under University of Maryland, Baltimore County. He earned his Bachelor of Science in Applied Physics in 2012 from Ateneo de Manila University in the Philippines, and then he did his PhD. He graduated in 2019 in Earth System Science under the Taiwan International Graduate Program, Earth System Science, a program under both the National Central University and Academia Sinica in Taiwan. And for his PhD, he did his research under Professor Lauren Chang from the NCU Department of Space Science and Engineering, as well as under Professor Liang from the Academic Sinica Institute of Earth Sciences. And then he did his postdoc research first with Professor Lauren Chang from 2019 until 2022, and then he joined NASA then. And his host at NASA is Dr. Dong Wu, and he primarily does research on astronomy, ionospheric physics, and solar terrestrial physics using space and ground-based observations, as well as first principles physical models. And so today he'll talk about using radio occultation to understanding ionosphere E-region response to solar and geomagnetic variability. So go ahead, Jude.
Thank you, Nick, for that introduction. So first, of course, thanks to you guys, and especially Cheating, for inviting me to give this colloquium. So I'll first acknowledge a number of folks that's listed here on my title slide who have been supporting me and helping me do this work on the E-region, especially, of course, as Nick mentioned, my host here at Goddard, Dong Wu. So here's just an outline of my presentation. So I'll start with, of course, an introduction, a bit of introduction on the E-region, why it's important. Then I'll be sharing our retrieval algorithm, how we're able to get these E-region electron density profiles from radio occultation. And then finally, I'll be sharing so far, what are the variabilities that we have been able to see or to observe with the data set. So starting with the relatively long time scales from seasonal to solar cycle variability. And then we'll make our way down to short-term variability until we reach hourly time scales during an actual geomagnetic storm, especially most specifically the May 2024 storm. Okay, so just a quick introduction on the E-region. So the E-region, it's the layer of our ionosphere between about 90 to 150 kilometers, where the electron density is primarily generated by a wide range of chemical reactions, but most especially the photodissociation of molecular oxygen and nitrogen, which is the two most abundant gases of our atmosphere. Now, why is the E-region important? So here I share just two simple reasons. So the first one pretty much encompasses why the ionosphere in general is important. So the ionosphere is important to a lot of our communication and navigation systems, especially now in a very modern age, that are reliant on sending a lot of these signals up into the ionosphere. The E-region in particular is important to radio wave bands in the MF, HF, and VHF bands. So our choice of these, no matter why you pick radio waves, right? What's with the specific signal frequency? So this is not some random choice that we have. So the appropriate signal frequency that needs to be used is, of course, dictated by the refractive index of the medium with which your signal is propagating. And the ionospheric refractive index is a strong function of electron density. And so it just so happens that the quote-unquote the common, electron density values in our ionosphere pretty much throughout the globe conveniently translates into appropriate signal frequencies of these waves. Now, however, during, say, a geomagnetic storm, right, when the electron density values start to bounce around really absurd, very strange, uncommon values, so naturally the systems will start to struggle because then you altered what the appropriate signal frequency is. So unless that system, predicted what it would be, they wouldn't know which signal frequency to work with, so it's not able to perform the duty that you needed to do. Another way of looking at this is one really good way to improve the system is just being able to predict these E-regional electron density values. So just that prediction alone can help a lot of these systems. The second reason I point out here is that, well, the E-region is home to a lot of ionospheric currents. So the interactions of the ions, the neutrons, the electrons here with the winds, magnetic fields, they generate these currents. And what we know about currents is, with the Faraday's law, we know that anytime you have a current, you get, magnetic field curling around that current. And these magnetic fields are able to extend all the way to the ground and interact with power systems, which are known to generate what is now called geomagnetically induced currents. Well, the role of electron density here is that anytime you have a medium where you have your current, so obviously you need to have some measure of conductivity in the region, and the level of conductivity of our ionosphere is a strong function, well, of any medium for that matter. It's always a strong function of composition, and so since electrons is kind of the dominant composition in the region, so naturally conductivity here is a strong function of electron density. So one of the really nice ways to be able to observe E-regional electron density is through the use of incoherent scatter radar. So here I share a 24-hour time series of E-regional electron density profiles from an incoherent scatter radar in Sanya over China, courtesy of our colleague Kokicha. So here you see some fairly well-known features of the E-region. So you get the high values during daytime and the low values during nighttime, which makes sense because, as I mentioned earlier, E-regional electron density is primarily from a lot of it is from photodissociation. So you get that solar factor really dominating much of the variability. At the same time, you see here this very interesting. Can you guys see can you at least see the mouse? Can you guys see the mouse?
Yes.
Pointing. Okay, good. Excellent. So yeah, you can see here this thin, high electron density layer forming. So that's called we're very well known phenomenon. It's called sporadic E. And I was initially thinking of, we're also doing work on that, and I was also thinking of sharing a little bit about that in this talk, but I figured it's too going to be a little information overload. So for most of my talk, I'll be ignoring that, but I'll just be focusing on everything else that you see here, which for our analysis we like to refer to as the background E-regional electron density. Now, as great as incoherent scatter radars are, one kind of disadvantage of that is they only give you like localized observations. Right? You can't get like a global scale look of the E-region using an incoherent scatter radar unless you're able to put that in everywhere from oceans and that. So it's just not visible. So which leads us to in our work, we try to get around this by using E-regional electron density profiles that we retrieve from radio occultation measurements. So here now I'll share a little bit about our retrieval algorithm and how we get these profiles from RO measurements. So to understand our algorithm, it's helpful to do just a very quick review on some basic principles of the radio occultation measurement principle. So radio occultation, it's all about trying to estimate space weather, terrestrial weather, or ionosphere atmospheric parameters from certain characteristics of a signal that is emitted from a GNSS signal on one end here from a GNSS satellite, makes our way through the ionosphere atmosphere, and is captured by a receiver in low Earth orbit. Now, what is this specific characteristic? So in first, just very layman's terms. So it's what you're doing with radio occultation is you're just trying to compare what the signal, a certain characteristic of the signal, that what it would have been if it didn't pass through any atmosphere or ionosphere. So it went through free space versus what it really is, as we observe it to be. So now, what is this specific characteristic now? So it's this thing called total excess phase. So a signal is being waved, so it has a phase, right? And as it's emitted by a GNSS satellite, we know what that phase is because it's a man-made signal. The receiver, on the other hand, it will compare that version of the signal that it captures with a version of it that, again, as I mentioned, passed through free space. Because of course the signal didn't go through free space. So if it went through free space, there should be no excess phase. That number should be 0. But of course, the signal didn't go through free space. It went through an ionosphere, an atmosphere, and even ionosphere goes out again. So naturally, there's a difference in phase, and that difference in phase is what we call total excess phase, and that is the crucial measurement that we need for our algorithm. Okay, now this total excess phase, it is a function of quite a number of parameters, but the ones relevant to our retrieval algorithm is that it is a function of the bending one, bending of the atmosphere. So here I express this as tau excess phase. So it's the sum of the bending from the atmosphere added to the bending due to the ionosphere, and finally this phase advance due to the signal um, simply propagating through plasma. So the bending, so it's just like any signal that you let it pass through two varying different media. So there would be a bending because of the differences in the refractive index of the two. So that effect on the excess phase, if initially, right, your excess phase was 0 and you let the signal pass through the atmosphere ionosphere, there's a bending. The effect there is you get a net positive gain, called net positive gain or increase in that excess phase. At the same time, as it passes through the ionosphere, of course, it's going through plasma. Now, the propagation of plasma induces a different kind of response to that excess phase. It actually speeds up, quote unquote, speeds up the signal, causing what you call a phase advance. So that one, for remember, excess phase, it's a negative net gain, sort of, so to speak. Now, my colleague Dong, in his 2018 paper, he has an appendix in that paper that shows the math, that stuff. But even without looking at the math, you can actually see that manifest here in the sample signal that I show. So here we pick a profile of excess phase, where you can clearly see that there's this local bump around 150 kilometers, and looking at the signal to noise ratio, that's the sporadic E, right? And you can see that, getting this, with respect to something, it's like a negative pushed back. So again, negative reduction in the excess phase. So here I just, and obviously now the sporadic E, whether it's E or the E region electromagnetic, that's also kind of a local bump there, but albeit a bit wider. So here you can see, that manifestation is very clear in this excess phase profile. So the reason I point this out is, one, I just want to show that, the E region's impact on the excess phase is a lot more apparent. Okay, it's not something that you have to kind of go through so much extracting of the numbers to see. It's very apparent. The tricky thing here is, how then do you ensure or isolate just the contribution to this of the signal passing through the E region electron density? So you have to remove bending from the ionosphere F region, right, and of course the passing through the F region, even some atmospheric bending, it might be there. So how do you isolate that one? So here I share how did we do that, how did we isolate that. So again, if you were to express the signal tau as the sum of the bending of the atmosphere and the ionosphere, and then its phase advance through the F region and E region. So the first step here, we try to remove the atmospheric bending. Now we take advantage of the fact that the bending is not a function of frequency. So if you have two frequencies of your signal, which is, fortunately, we do have that, so the L1 and L2 GNSS signal, you can subtract the two signal. It leaves you with a version of the signal that's removed that atmospheric bending. So that's what we do with this one. Now the next step is, of course, to remove pretty much the other ionospheric stuff. So F region bending, F region phase advance, and F region bending. Now the E region bending is owing to its short path length. We can assume that that's that's reasonable. So that's very small. So we kind of ignore that. The F region bending and phase advance. So okay, this is what is key to our method. So from some simulations using an RO model, where you give it an electron density profile, so IRI in this case, and you get an excess phase profile. We found that, my colleague Dong, what he found was that the contributions of F region bending and F region phase advance on this excess phase profiles can be captured, or is a linear function of tangent height, and that function you can kind of estimate using values here at the bottom, below 80 kilometers. So that's why we call it bottom-up method. So you estimate that linear function, and then extrapolate all the way up to the E region, and then subtract that value. So that was with some simulations before, but I actually kind of get a hint of it in just looking at this excess phase profile where there's that tilt. So, but fortunately, some modeling was able to support this important trick of the method. So once you do that, you remove it, and then after that, you just convert. So the excess phase, the conversion to horizontal total electron content, that's fairly well known. And then from there, you're able to solve electron density. In our case, we use the optimal estimation method. Now, the optimal estimation method, that's a fairly well known if you do nonlinear inversion stuff. And that's fairly well known. So I won't go into too much detail on the nitty gritty there. So I'll just refer you guys to the retrieval algorithm paper, Wu et al. 2022 for that. But really, the crux of our method was in the previous step. How do we isolate that E region electron density, or the excess phase that's solely due to E region electron density? So just a comparison. So prior to this method, there's the more well-known method, the onion peeling method. Now the onion peel method, what it does is, at least in its simplest summary, it also takes the excess phase, right, and then converts it directly to H-stack, and then performs the onion peeling method per layer. It's called onion peel method, but you do is you're inverting using this Abel inversion per layer. If there's no uncertainty from the top all the way going down, this is still definitely the method to go. But unfortunately, as is very well known, you have a lot of uncertainties above there, and so as you're going way down, that just explodes. And then it's what that is causing is once you reach the E region, you get a lot of very unphysical values. So if there's a main difference between our method and the onion peeling, is that the first part, the very first step, is we try to isolate the E region before performing any other, when you convert to H stack and then get the electron density. So two important notes of our method. One, okay, absolute magnitudes. No, are we God's proof? No, we're not. Okay, well, at least so far from our comparisons, we are within reasonable range of other instruments and also models. Definitely, compared to the onion peeling method, at least we are able to minimize the retrieval of very unphysical values. But again, in terms of God's truth, there's definitely a lot of work that could still be done to make us really reach that level, and we have planned tasks for that in the coming months ahead. On the other hand, for looking at morphologies, we're pretty confident in what we can see here, because what you're really just doing here is analyzing this bump that you're seeing here, right? Even if you don't turn it to electron density, just analyzing that, you're already going to capture quite a lot of the E region electron density variabilities here, because that part is very apparent. Another way of looking at this, if the only way for this would be wrong, is that if there were someone to come in and say that this bump is caused by something other than refractive index, which is a strong function of electron density. In which case, even if you use the a perfect version of your onion peeling method, it would still not. Okay, so far, what are the variabilities that we have been able to observe? So I'll start with, again, so a relatively long time scale. So seasonal and solar cycle variabilities, just quickly go to some highlights of what so far we've seen. So the contents that I'll share is actually contents in our paper that we published last year, which was actually centered on an empirical model that we developed that accounts for these variabilities. So I'll be sharing, so in this section, I'll be sharing kind of, I think, two birds with one stone. I'll be sharing, of course, the variabilities from the observation. So in this case, it's mostly from Cosmic 1 data. And then also how it manifests in our empirical model, which was constructed solely based on Cosmic 1 data from 2007 till 2016. So those interested in using this model, so this is in a GitHub page. The link is shown here. So okay, just very quickly on the model. So we call it the E region prompt radio occultation based electron density model. So if I can highlight one bit of this architecture, is that its architecture is based on this finding that we had, that if you were to take, say, construct a monthly mean latitude, local time, altitude profile of E region electron density from the data, and then over each latitude, local time grid point, right, a vertical profile, and then you fit that with this modified Chapman function that I show here, where you're just doing a nonlinear fit with three parameters, this NME, HME, and H, and then reconstruct that whole profile. You can actually capture, as shown here in the subplot C, almost 100% of that whole profile's variability. So our model is really to simulate E region electron density. We're just trying to simulate as much of the variability of these three estimated parameters. So for more on the the expressions, I won't show it here, but I'll refer you to our paper on that one. But so what did the model and of course the observations show? So here, the first one I just highlight, it's about something with a seasonal variation. Okay, so here there's 4 subplots. So the subplot A, this is Cosmic 1 June 2007 E region electron density profile, longitude, latitude, so at 12 UTC, 100 kilometers. B is the empirical model, so how captured that one. The one at the bottom is C is from IRI, and D is Wacom X. So now with the seasonal variation of E region, the, to the best that we know so far, because of the sparse measurements, it's usually typical models of E region electron density kind of just treated as though it's mirroring the solar zenith angle, wherein you have that high value. So this is June, right? So you have the high value of the summer, and then that curvature is just following the solar zenith angle. So it goes lower as you shift. Maybe there's a local high in the tropics, but and then on the winter it should be low. Clearly here in our observations and the model, you see that in the winter poles, it's relatively higher. IRI does not show that, which again is not surprising because IRI is based on those ground-based observations and it just treats E region electron density, as I mentioned, like a mirror of solar zenith angle. But Wacom X does. So you see here this local peak also. Here, what we just point out is at least it gives our observations and model is in support of variabilities in the E region that is not purely explainable by solar zenith angle. So in this case, this could be neutral dynamics thing. So we haven't done too much into analysis of that because in this paper, this was more just a model presentation and validation. But yeah, I would not be surprised if when I'm able to look at the model, about this one and see that's probably a dynamics thing. So another nice angle here is the zonal profile. Again, this is in June. So you can see over the summer, generally high values, but then over the winter, you get those two local peaks. So one over the 60 degrees south, which that's captured by Wacom X, so indicated that's probably maybe it's a geomagnetic, geomagnetically driven structure. So, but yeah, so with these two comparisons, so our highlight here is that our observations and empirical model are in support that the E region, it's not purely solar zenith angle driven. There's a lot more that could be driving the morphology there, unlike is typically assumed with say IRI model. Now the comparison with Wacom X isn't all good. There's one I highlight is the solar cycle of variation. Here, the plot below, the red is Wacom X, and all the other ones, IRI, Cosmic 1, in our model is the ones mixed here. It's apparently lower. The amplitude a little close, but yeah, the values are quite low. So why that is, we're still not sure about that one. Now we did also make sure to do some comparisons with observations. So here I just show our results and comparing with some ionosons. So with ionosons, you're typically limited to daytime, but we try to make the most out of whatever ground base we have. And the ones at the top, this is from manually scaled ionograms, and the one from below is auto scaled. So that's why the manual scaled here we don't split into months because actually it's very limited. Because doing the scaling is very tedious work, so we just make the most out of what we have. We work with 4 stations, one in Hermanos, Fortaleza, Ichon, and Gacona. So 30 degrees south, 3 degrees south, about 37 degrees north, and then 60 degrees south. And what we just show here is that at least our vertical profiles, they are within reasonable range of the ionosons. We also compared with some radar observations. So from Arecibo and from Millstone Hill, and I guess if I'm going to put a highlight here, it's the nighttime values. You can see relatively lower values from the radar compared to our observations. We have some planned analysis on that one on why that is. But again, this is just consistent with what I mentioned earlier about the absolute magnitude. There's definitely still room for growth there. But morphology wise, we're pretty confident that. And yeah, well, this is just showing that the diurnal variation here. So for this section, so just a quick summary of this subsection. So yeah, our model and observations do support Wacom X in that there's a lot of variability or morphology or structures in regional electron density that can't solely be explained by solar zenith angles. So we kind of got a hint here of maybe neutral dynamics being important in the winter or even geomagnetic forcing. And then, of course, as I mentioned earlier, the nighttime disparity. That's still definitely something that we're going to be investigating a bit more, taking both sides into account. Radars themselves, they aren't perfect measurements. They're also assumptions there. So we'll play with both sides and kind of play devil's advocate, in all these instruments and see, which it would be. I think that's going to be an interesting investigation we'll be doing in the coming months. Okay, so that's month. Yes, is there a question?
Yeah, I think there's a couple questions.
Oh,
Yeah, can you go back? You 3 slides and one more. Yeah, what's the red line and the blue line? What
Oh.
do they stand for?
This blue, the vertical
No,
blue line.
No, there's 2 lines.
Oh,
Yeah,
these 2 lines. Okay, so
Yeah.
these 2 lines, this is the average of all. So each station, right? We have multiple profiles. So we over each. So there's the time of that when it happened. So we ran our empirical model over each of those exact dates, and then average them, and then the error bars is just the standard deviation. So what this is just showing is like how well the average is comparing between the ionoson and our empirical model. The difference between the top and bottom, the top is those profiles were manually scaled ionograms, while the one below is by a software. So it's more profiles here, but also and I'm not expecting ionoson. So this is, by the way, courtesy of our colleagues from Air Force. So they're the experts on this. So in simplest way, these auto-scaled ionograms, sometimes they might not be the best, but we just made the most of whatever the data we could get, and just tried to see the comparison anyways.
Jude, for this run of WACMAX, are you using F10.7 like UVAC, or you use the what's the Phil Chamberlain's model? What's it called? I forgot.
FISM.
Yeah, FISM. Yeah. Well, which one did you use for?
So I think this
You
one is
guys-
just I think this is just F10.7. This is yeah, actually I didn't run this. This was stored. It was already in the Cheyenne the virtual computers.
I
So
see, okay.
but I think it was standard as the Wacom X runs.
Okay, thanks.
Any more questions?
I think you can keep going.
Okay. So that's monthly variability, right? So solely using Cosmic 1 data. So now let's go into day-to-day variabilities. So here, the results here are one, it's the geomagnetic stuff. It's published in a GRL paper early this year. And then the second one, it's on the solar rotation stuff. This is currently in revision for resubmission. So the previous section, we used mostly Cosmic 1 data. For this part now, so this was enabled by more recent RO measurements, specifically from SPIRE and the Cosmic 2 measurements. So with SPIRE RO in 2022 and 2023, they were providing up to 15,000 profiles per day. And that translates, so the plots I'm showing here, this is the sampling in 1 hour universal time. So just 1 hour picture of all available profiles. Here on the left, this is SPIRE, and the one on the right is Cosmic 2. So with SPIRE RO, that 15,000 profiles per day was apparently translating to about 600 to 700 profiles globally in 1 hour. Cosmic 2 is 7,000 profiles, but this is just at the low latitude. So as you can see here, although number is lower, but because it's just situated in a narrower latitude, so it still gets really good coverage. For comparison, Cosmic 1 was only giving us 2,000 profiles, which is not in any way meant to put down Cosmic 1, because I think we all agree these more recent RO missions would not have made it through if it weren't for the success of Cosmic 1. But this is just to show, how the progress and this work with RO, how good the sampling is right now. So, with this kind of sampling, so I think I've heard a lot of folks in the audience, and those doing atmosphere ionosphere coupling, you'd first think, oh wow, this got great sampling. Let's look at planetary scale waves and stuff. But I said, okay, you know what? Let's go first for variabilities that also act to kind of validate the data. So I was thinking, okay, what variabilities I know if your data is really, as you say, it is in the, as I mentioned about morphology and stuff, it's really there. These variabilities should be there. If it's not, then better start thinking twice about your data. So this is why I started with looking at very simply just the solar rotation signal, because in the E region, low latitude daytime, that should be there in your E region. Whatever data you have, it should be there. If it's not, start questioning it. So that's why I started with this solar rotation. So is it there in the data? So yes, fortunately it was. So here at the top, I show a time series in blue. So I averaged all Cosmic 2 data at 110 kilometers between magnetic latitude 10 degrees south and 10 degrees north, and 9 a.m. till 3 p.m. every day. So each dot, that's an average. And then I overplotted that with the Prism 2E EUV flux, but you can use lim and alpha or f10.0, whichever, it's fine. Here, the only thing I removed here in this time series was the seasonal variation. I kept the mean there, and you can see how nicely it's following the EUV flux. And if you do the wavelet spectrum, you can see quite nicely here in 2022. Visually, it's pretty clear. In 2022, that those cycles are very nice and pronounced, and it's, you know, it reflects quite nicely in the wavelet spectrum to be the solar rotation signal. Spire, on the other hand, which is here in B, apparently it's noisier. You can see a bit about it, but it's relatively noisier, and we attribute this possibly to just an instrument thing. With Cosmic 2 being a microsatellite, the GNSS instrument, that was a large one, and I believe it can even move around to give you the best capture of every signal. Spire, for the most part, it's all of it, I believe, is CubeSat, so the limb, so it's much smaller. So we think that could be a factor in there. Here I just did some statistics with the EUV. So again, this is nothing new here. This is something that should be, if your data is good, it should be, you know, E-region daytime, it should be well correlated with EUV. And that's shown here quite nicely. Even with Spire and its relatively noisier values, it's still there, 0.9, 0.97. Below, I just do a running correlation, 30-day window, step daily, to kind of get the correlation and then be able to quantify how much the solar rotation is contributing to these day-to-day variabilities. And we calculate it's about 60 to 80% of that. Despite Spire's noise, we still, you know, decide to shoot our shot and see seasonal variation with the thinking that since solar rotation, obviously it's a solar-driven thing. Maybe it should be more apparent with summer and not in winter. So there should be a seasonal variation. Quick answer, apparently it's not. So we don't know, maybe it's a noise thing, but it's definitely not very, very apparent in the time series. Now, with those plots, I just showed one dot, right, average. So I thought I'd challenge the data even more and say, okay, what if I produced a map? So obviously with Cosmic 2, because it's clearly Spire is a bit noisy, but with Cosmic 2, can I see it? If I plotted the map daytime, constructed the map, and then looked at the full 30-day cycle, would I be able to see that gradual enhancement in the values throughout the map? So here, so obviously I can't really show 30 days worth of plots because that's a lot. So I just show here for one solar rotation cycle sometime in the mid 2022, every 3 days of the cycle, and I put the peak of the cycle here in some plot E. And you can kind of see quite nicely, you know, as you approach that peak, things start, there's a growth in the values until it peaks, and then it goes down as you go, you know, towards the descending end of the cycle. So that's for solar rotation, daytime. Okay, that I figured, okay, that was one thing. Okay, now how about nighttime? What could be something? And well, the first thing that was, I think, pretty obvious was geomagnetic force. I mean, despite, so here I just use with Spire RO, so obviously this is high latitudes, but still, you know, if Spire RO cannot see this, at least even a hint of this geomagnetic forcing, then yeah, I'd say it's really going to be hard to justify the use of Spire RO in any other thing. So is this correlation with KP index in particular? Is it there in Spire RO observations? Well, it was published, so it kind of spoils things. But yeah, so here I first show, I construct every day a zonal profile from 2021 till 2024 using Spire RO data, nighttime. So from 9 p.m. to 3 a.m. every day, right? I have a snapshot of that. And then at each grid point, I just did a correlation and regression with the KP index. So fortunately, yeah, you can see here nicely the high correlation in the auroral latitudes, with even some hint of something interesting going on in the southern area, where there's a local peak towards the mid latitudes and a bit more towards the poles. So I thought that was interesting. But although we haven't gone into much depth of those interesting new features, but yeah, at least we're very happy to have seen. Okay, there's that good correlation on the auroral latitudes, which is something you want to expect from our data set. The ones below, this is just a scatter plot, just to confirm, just to show that yes, that if you took one, you know, time series there, do a scatter plot at so this is southern auroral oval between 50s to 70s, and northern auroral oval between 50n to 70n. So you get that nice correlation, just to show that, yeah, well, what you're seeing here in the map is supported by a single scatter plot. So now you ask, okay, how about from a map perspective? What do you see, right? Still, you have enough data. If you, instead of zonal profile, let's look at a map. What do we see? I'd like to think even prettier. And this is probably one of my favorite plots that I made recently. So yeah, here I can show you the correlation as a map, right? So very nicely, it's following the curvature of that auroral oval. So obviously, if you plot this in geomagnetic latitude, it straightens up, but over the map, it's quite nicely following that curve of the auroral latitude. So the top is just the correlation, bottom is regression coefficients. But yeah, it's nicely following that one. We've checked this with Wacom-X, and this is also consistent with what the model is showing. The one on the right, so this is Cosmic 2, and it's showing something even more interesting, although we haven't gone into too much depth on this one. This was not reported in the paper, by the way, because we haven't yet found a model that's able to see this. But yeah, there's apparently some negative correlation extending down to the low latitudes, and it's not very high, but it's correlation is suggesting it's statistically significant. So we don't know yet what that is. That's one of the things we're going to be looking at in depth the coming months. So, okay, as I showed earlier with the solar rotation, can I also see this if I make the map, right? Or is this just the artifact of the correlation stuff? So here I center on the May 2024 storm that day, 132 I put here at subplot E. So this is plus minus 4 days of that, of this storm. And yeah, you can see quite nicely, days before that, very quiet, nothing. And then as you reach the day of the peak of the storm, the brightness really even quite nicely follows. And this isn't even very high resolution in the map. The grid here is like 5 by 30 degrees, 5 latitude by 30 degrees longitude, but still it's following that quite nicely. And of course, it goes down a few days after the storm. How about daytime? What's going on in the daytime? So here I just showed the correlation as a function of geomagnetic latitude now and local solar time. So the nighttime you can see here is consistent with what I showed earlier, so high positive correlation. But in the daytime, you see the values start to move towards the mid latitudes, and then it's negative, a negative correlation. And that is what I will discuss in the next section. So hold that thought. So just quick subsection summary here. Yeah, with the solar rotation, geomagnetic activity, fortunately, the data was manifesting it, get good correlation. So this 50% with the geomagnetic activity, if you account for the noisiness of spire, maybe there is an underestimation. At least morphology, it's showing, it's manifesting itself. So that gives us some, it gives the spire data a bit some credibility on that regard. So now we go to hourly variability. So here, the highlight connects to that thing I mentioned earlier about daytime being a negative. But here we probe a bit more with a storm. So, and obviously a storm, that's not a daily variability thing. That's an hourly time scale phenomenon, right? So here, that's where we go into now. But can we use with the data, can you, really give you that hourly time scale resolution? So in so this is centered on the May 2024 storm. Unfortunately, in 2024, the spire arrow data dropped in number of samplings from, as I mentioned, 15,000. It went down to 7,000 profiles. And so now it's down to like 300 profiles globally, which isn't really good, as shown here in subplot A. So it's not as well distributed, and unlike, say, Cosmic 2 here in B. So, but we use this as a kind of motivation to know, okay, maybe we can think about merging the different data sets. And in addition to Spire Arrow and Cosmic 2, we also merged data from a Chinese mission satellite constellation called Fengyun 3. So we were able to get their RO data, level 1B RO from that data, so it's public. So we're able to download that and work with those data sets from Fengyun 3D, E, F, and G. So 4 satellites of RO data. Combining the 3, so you get here subplot D, this is the sampling that you would get by merging the data. Now, of course, when you're merging different data sets, you need to make sure you try to remove as much as you can the biases of the different data sets with one another. So for these 3 data sets, we corrected Fengyun and Spire with respect to Cosmic 2, simply because in terms of instrument, we think, and I believe RO experts on instruments would agree with this, that instrument is really the most, at least the superior of those 3. So how did we correct the 2 data sets with respect to Cosmic 2? So the first step here, so for each month, we constructed a longitude, latitude, altitude, UTC altitude profile of E regional electron density. And at each altitude, we do a scatter or a correlation that's shown here, a sample here at 1 altitude that's shown here, and then fit that with a straight line, so a linear regression. And then the the y-intercept is the bias, what we call the bias, and then the slope is what we call the scaling factor. So we just repeat that process for all altitudes and months where the data sets coincide, right? And then just take the average of that. So we do note the standard deviation that's shown here below now. We see that, okay, they're not too far off. The standard deviation isn't that too large. So we use that, we at least use that as support that we can work with this blue line, these two blue lines, as our correction, what we call correction factors for the data set. So we repeat this process for Spire and then for the different Feng satellites. So I guess a big difference with the Feng satellite with the Spire is that with the Feng, because each satellite is kind of very distinct instrument, so we had to separate this process for each satellite and not do like combine them and use the same factors because there's quite the difference there. So we did that. So we combined that, and then this so far right now is our main highlight. So with that data set, we're able to produce this longitude profile time series, hourly time series. And the highlight that popped up when we were looking at this is that, well, here you can see, okay, so you can see the general stuff you expect in the E region, the high values during daytime. But during, so I overplotted with this with the DST index during the storm. You can see here, during the storm, but the main to recovery phase, there's a relatively low daytime value. And this is averaged between 20 degrees north and 40 degrees north. So basically the data set is suggesting that during the daytime over the mid-latitudes, there is a reduction in E-region electron density, which is consistent with what I showed earlier about the correlation, although that one was more day-to-day variability. So here we confirm, if you look at the specific storm, at least for the May 2024 storm, you can see this reduction. Note though that this feature, you might think, okay, maybe this is still an artifact of our merging of the different data sets. No, it's not. If I show you the same plot, but from Cosmic 2, so obviously a bit more white spaces, indicating no data, but most of it is conveniently in the nighttime. So the daytime was still very clear, and you can still see this reduction. So that gives us confidence that what we're seeing here is not an artifact of our attempt to merge the data sets. To further isolate it, so at each hour, I averaged the daytime only from 9 a.m. to 3 p.m. and then construct a time series. So that's shown here in subplot B. So overlaid again with the DST index, and here also even clearer the negative drop in E-region electron density profile, in E-region electron density values. So below is just some statistics, so just the lag to see how much, about a few hours, and it's pretty apparent here in the time series. It takes a few hours for their kind of peaks to match, and then using that lag, we did a regression just to quantify how much things change with respect to 100 DST index, so about 8% per 100 DST, which is consistent with what we see here, right? So this is about 400, negative 400, so times 4, so 30, 40% of that one. So, but question is, what's driving this one? So, well, is there a model that can at least simulate even just a bit of this variation? Fortunately, GIE-GCM, just using a run where I kept the F10.7 or the solar F10.7 constant and just let the geomagnetic index vary, is able to reproduce this variation, albeit at quite a weaker level. So the subplot A here is the same as the subplot A before, and you can see it's not very apparent if you don't remove anything. I had to remove migrating diurnal, semi-diurnal, and terdiurnal tides to kind of isolate that. And then, yeah, once I do the time series thing here below, it's only like -2, -3% reduction. Nevertheless, we still take advantage of the model and try to diagnose it to at least get some idea of what it could be, because then at the same time, we can potentially give our own suggestions as to what improvements we could give the model. So what drives this reduction in E-region density, the daytime E-region density over the mid-latitudes during the May 2024 storm? So I did a model diagnostic. So we know that with ionospheric electron density, models usually it's just the sum of relevant positive ions. So in the E region, it's the O2 plus and NO plus. So to confirm that if you added O2 plus and NO plus density shown here, you can reproduce that. So yeah, I showed here. So this subplot A is very similar to the plot I showed earlier. So just confirming that yes, whatever is going on, it's got something to do with O2 plus and NO plus. So next question, of course, is okay, so which of the two is experiencing this reduction. So we found that it is O2 plus that is undergoing a reduction that's shown here in subplot B. NO plus is showing an enhancement, but I think that's a very well-known response of NO plus during storms. So focusing now on O2 plus, so we know O2 plus in the region is mostly from the photodissociation of molecular oxygen. So naturally, we looked at what's going on with molecular oxygen, and that's shown here in subplot D. You can see very clearly there's an almost drop in molecular oxygen during this storm. So next question, of course, is okay. So what's going on with molecular oxygen in this region? So I did a term analysis, where I broke down the continued equation for this O2 species. I was looking at horizontal advection, vertical advection, fusion, chemistry, and such. And I don't show it here, but in a nutshell, basically what I saw was, surprisingly, it's O2 here is really predominantly controlled by vertical advection. So naturally, I looked at the vertical wind, and yeah, you can see that there's this predominantly downwelling that's occurring. There's some instance of upwelling, but generally it's a negative, value that's occurring here. So then what is going on here? So I did a correlation now of the meridional wind and the vertical wind with KP index for the May 2024 storm, and what it just shows here is that this at 110 kilometers is just the lower most boundary of this otherwise fairly well-known circulation that's occurring during a storm, right? So it's the heating and the auroral latitude is pushing like a fountain circulation, equatorward, poleward, and such, and of course some of it has to go down. So that's this downwelling here, and so it looks like that what's going on at 110 kilometers is just the lower rung of that. Now, at first look, this seems to be in contradiction to what gold is showing. With gold, it's suggesting, so gold is looking at ON2, and with a lot of the analysis that was done there, it's suggesting that N2 should be positively correlated with the KP index. O2 having the same, and that positive correlation is a result of the the expansion, right? O2 being similar vertical profile, you should expect something similar. So I went into the model and looked at the correlation of O2 now as a function of altitude, and I was surprised to see here in subplot C that what gold is suggesting, it is correct. But gold is showing things at 130, 150. And I guess we have this kind of tendency sometimes to just assume that it's got to happen the same thing at 110 kilometers. They're not too far off. Apparently, and this is according to the model, there's a big difference in what controls O2 in just this 20-kilometer difference. So above that, yeah, gold is correct. That's all true. N2O, N2, O2 and stuff, that's positively correlated. But below that, it's not, it's negative, because as I showed earlier, it's more controlled by vertical advection. And my explanation there so far, I think it's probably with the gradient. I look at here, so this is the mean O2 here, average throughout the storm. You can see that there is still a relatively higher gradient down there. So at least that's what I think. Maybe that's a factor in why below here you still have the vertical advection outwitting in chemistry through temperature. So yeah, just an illustration of this mechanism. So without any storm, you have the very basic generation mechanism of the E region, right? You have high O2 air below, most of it being undergoing photodissociation, producing E region electron density, which is pretty much like the basic generation mechanism of the E region. Above that, you got the low O2 air, actually. During storm, what we're seeing here is, at least according to the model, there's a circulation that's pushing things down, and you get that low O2 air that's pushed down into the E region. And so since O2 is an important source of electrons there, so naturally we're also reducing the E region electron density during the storm. So yeah, subsection summary. So our data set and simulations do show that there's a reduction in daytime E region electron density over the mid-latitudes during the May 2024 storm, and that the model simulations are suggesting that this is connected to the downwelling that's occurring. Given that the comparison showed that it looks like the model is underestimating this, so maybe this is an indicator that downwelling is still being underestimated. Unfortunately, obviously, unless we have observations that's flown up there to confirm these things, that's really the most we can do. It's hard to really pinpoint which is wrong, but at least we have something to start with in terms of what can be improved in the model. So okay, to end, so yeah, just conclusion so far what we've seen. Our data set is manifesting variabilities, a good mix of things that should be there, at least from solar and geomagnetic force variabilities that should be there, if the data is reasonable. And even adding in some new things like this May 24 storm that's still though supported by some physics-based simulations. And last, our sampling I think is really, really good. I only shared 3 data, but we have the RO data from so many different missions, MetUp, Korean CompSat, so many that we download through CDAC. So we just get all that and do the retrieval. So with that sampling, we can really explore a lot of these variabilities. It's just that we're taking it, bit by bit, incorporating, right? Because as you add more, when you're merging data, it's always a tricky business. So you want to be careful and make sure things are performing, because sometimes maybe you insert a new data there and things blow up. So we're in the process of doing that. So future work. So now that we have at least the expected variabilities are there, so at least we have more confidence in proceeding into now looking at things like planetary scale waves and stuff, and never know, with more data coming in, more years, so you can even look at interannual phenomena. I mentioned this earlier, so we are looking also at sporadic E variability, and in fact we have a World Day Radar campaign for this next year, where we're gonna look at sporadic E perturbations on ionospheric E regional electron density and consequently conductivity during the Perseid's meteor shower. Okay, so I guess this is the sad part. This is supposed to be a nice animation. Yeah, this is just part of our Living with Star grant. And to end, just acknowledgement on the funding. So Just Star 2's cooperative agreement, that's a Living with Star grant that we were able to get it spans from 24 to 2028. And then last year had internal support in the university through a grant. And then of course, the SPIRE RO data is only made possible through NASA's commercial satellite data acquisition program. Thank you.
Okay, thank you, Jude. Does anyone have any questions? Sergey, why don't you go first?
Okay, thank you. Thank you for the presentation. It was very condensed. My question is about very first section. It was difficult to catch all details, but I want to understand some fundamentals. Fundamentally, excess phase is known up to uncertain constant. Unless you have measurement when your line of sight goes outside of any refractive medium and you can connect the phase, you cannot solve for that constant. In order to derive absolute TEC from excess phase, you need additional assumptions, approximations, measurements. Would it be possible to outline without details what were those assumptions, constraints, or whatever which allow to derive absolute TEC from excess phase?
Oh, okay. Yeah, that's a very detailed question. I could, because this was Dong who did the nitty-gritty of this one, so I just tried to give a an overview of the whole algorithm. I could get back to you on that one. Yeah, sorry, because this part is really Dong was able to one who really did the nitty-gritty, so I just tried to give a brief overview. Yeah, I believe you mentioned a little bit about that, but yeah, I don't think I can give a very definitive answer on that one. Sorry about that.
Okay, well, thank you anyway. Thank you.
Yeah, to do the oral part, I mean, it's second section, there's a slide if you could move forward.
Sorry.
Yeah, move forward with the second subsection.
Oh, second subsection. Okay.
Yeah.
This subsection, right?
Yeah, move forward. There's a word. Go forward. That means I can say move forward. Go ahead. Yeah, this one have first question.
This one. Yes.
In the lower latitudes, the form Cosmic 2, looks to me your E region electron density also so kind of low density along the magnetic equator, and it looks like peaks in the EI region or in the F region signature, which is a pretty surprise to me or something like that.
Yes.
I don't know why there's a signal of those things. This is you use a bottom up, so not supposed to have F region signature here, right?
Yes. Yeah. No. This local. Yeah, you can see it's following the magnetic field, right?
Yeah.
And this is definitely something we are going to be looking at from that angle. Because one, we tried to see maybe this is real physics, and so far there's no model that's able to really show this. The longitude variability, the Wacom X shows it, but it's that thing where it's following along the magnetic field line, that local minimum. It's really, yeah, we can't see this. So something we're going to be doing is, well, retest that F region assumption that we have. Maybe that could be still seeping in there. This is why I mentioned earlier, about the absolute magnitude that could still be a factor. So right now we do not have an answer why there is that local peak in the magnetic equator.
Okay, if you move forward with the auroras, here.
Oh, this one.
Let's go back. Yeah, this one. In the northern hemisphere, you have one peak at about 60 degrees.
Yes.
Whereas in the southern hemisphere, you have two sub-peaks. So I believe 75 peak, I can understand that one.
For some reason,
Yeah, but at 30, 40 degrees, that peak, I don't know why that occurred. What is that?
Yeah, no, definitely that peak so far we have not also seen it in model. So yeah, this is one of the things definitely that's not sure why there's that local. I mean, it's not very high. It's 0.2, 0.4. But yeah, for nighttime so far, this is why we shifted now to hourly variability during the actual storm, so we can really see. So far, it's also not there. So maybe it's definitely still a question. We're still not sure why that's popping up when you look at day-to-day variability.
Okay, thank you.
Michael, did you have a question?
Yes, I do. From your presentation, I take that you are pretty confident that the measurements are very precise. So with respect to the discrepancies between your physics implied from the measurements and the models, is it your judgment that this is an issue of model tweaking, or is there any substantial physics missing?
Okay. Yeah, a very good question. I would say there's definitely in our models right now. Well, to Wacom X's credit so far, and even TIE-GCM, it's a lot of it's getting captured. But there's definitely, I think, maybe an underestimation of certain. I wouldn't say exact mechanisms, possibly, but it's definitely there's room for the model side. But we also try to assess on our side the observations. Maybe there's also something there, so we're kind of push and pull between the two. But with the E region, when it comes to modeling, I mean, our data sets were very limited, to ground based. So it definitely shouldn't be surprising that there's a lot of stuff that's still needs to be added in these models. And I believe, although here I showed some good performance with Wacom X and TIE-GCM, I know the E region lower ionosphere there is still relatively simplified. There's still a lot that needs to be developed there. I know there's some attempts, for example, there's that just the chemistry for one. I know there's a different variation of a version of Wacom X, like the MAD, the middle atmosphere D region stuff and stuff. So it's definitely, I think there's still missing stuff in the model that hopefully with these observations we can help improve.
Thank you.
Dude, I do have one question as well.
Yes.
On the May 2024 storm, you mentioned a sort of difference between the RO observations and gold.
Yes.
And part of that was altitude difference, because I think you were looking at the lower altitude. Can you look at a slightly higher altitude in your observation, or they don't go up to 130 something?
Okay. Yeah, we can. Actually, we do have F region, and we've cross-checked it with TIE-GCM, and interestingly, that whole mid-latitude daytime, it is undergoing a reduction. All the way F region, we looked at 350, I think 250, 200, because we have other from pod data. yeah, and TI-EGCM is also showing that it's also negative, but of course the driver is going to be different, right, at each altitude. So I don't know which ions is probably going to be factored there, but yeah, we definitely can.
I was just wondering at what altitude is the observation tell you where it sort of switch?
The
Like
you
in the
mean
bottom left here, you kind of
Uh-huh.
show 120, they
Yeah.
switch. From the observation, if you can see anything.
Oh, okay. Well, because our observations with electron density, it's all showing a negative reduction. We don't have O2 data that can give us that same thing with, yeah. So I can't really see where that switch happens.
Any other questions? Okay, thank you again, Jude.
Thank you. It's like